Hey YouTube, today I wanted to talk about spanning tree protocol. Spanning tree protocol can also be said as STP. It's a protocol that is needed to stop loops in a switch network. And what is the case where this might happen? Well, let's say we need even more ports from like the last video where we had two switches and we need to add a third. This third switch will have a trunk to both switch 1 and 2. This will create a loop in the network. But why, you may ask? This is the first time we need to understand a little about how a switch network works. A switch has something called a CAM table. It's the content addressable memory. This table stores information such as port, VLAN, and MAC address on the interface. A MAC address is another new term. A MAC address is the media access control. It's a 48-bit written in hexadecimal that is burned into an endpoint. The first half of the MAC address is the OUI, which is the Organizational Unique Identifier, that is assigned to a company that makes network devices. Now this OUI can be used to look up a manufacturer device, which can be useful from time to time, especially when troubleshooting or trying to find a device. And this burned-in address's second half is assigned by the manufacturer to the device. So on a Cisco switch, you'll see the format something like the following, where it might be 0AB3.241F.E083. So this MAC address is stored in the CAM table, which allows the switch to move the frame between ports. Now the CAM table builds this data by receiving frames. So the frame will contain a source MAC address and a destination MAC address. So when the switch receives the source MAC address, it saves it in this CAM table with the port and the VLAN it's assigned to. And it should look something like this. So let me type out show MAC address table. You can see it has the VLAN, the MAC address, and the port. So that's the basic idea of how a switch can learn a MAC address and how it switches frames. However, what does the switch do with a frame if it doesn't know what port to send it to? This is the case of what's called an unknown unicast address. And what the switch will do is broadcast that frame to all the ports a part of that VLAN, except the port it came from. So a switch will broadcast an unknown unicast frame and a broadcast frame. And the format of a broadcast frame is FFFF.FFFF.FFFF. So it's just 255, 255, 255, 255, pretty much. You know, it's the highest if you look at IP addresses for broadcast. Now, a common application that will send out a broadcast packet is ARP. And ARP stands for Address Resolution Protocol. And what that does is it sends a broadcast from an endpoint asking for the IP to MAC resolution. So an endpoint might want to communicate to another device on its same subnet. And if it has never communicated with that device, it sends a broadcast asking, does anyone know this IP? Do they have it? And the device that has that IP will reply with an ARP reply, and that ARP reply has the MAC address of the device. So the endpoint will learn the MAC to IP, and then it can send directly to that device. So during this whole process, the switch is building its CAM table and will know the ports to which the endpoints are on and can switch it directly without broadcasting again. Okay. So that's been a lot of talk about MAC addresses, CAM tables, ARP, but I said this video was going to be about spanning tree protocol. Why was that all that I mentioned then? Well, without spanning tree, what can happen is, let me show a picture. If a frame is broadcast, it can begin to loop. So switch 1 broadcasts a frame on all of its ports on the same VLAN. It will also send out both trunks to the other two switches. Then switch 2 and switch 3 will receive it, and it will broadcast it and continue sending it all around. Eventually the switches will keep sending the packets, the CPU will spike to possibly 100%, and can bring traffic down to a crawl, or if unchecked, it could even crash a switch. So that's where spanning tree protocol comes into play. It will block one of the ports to keep a loop from occurring. Well, how does it know what to block? Well, the switches perform an election to see who is going to be called the root bridge, or a root switch. And what the switches do is send something on all trunks to each other called a BPDU, or a BPDU, whatever you want to call it. It's a Bridge Protocol Data Unit. This BPDU has some information in it, like bridge priority, which the default is 32,768, and the MAC address. The switch sends these BPDUs to each other and chooses whoever has the lowest priority, and if they are all the same priority, then it chooses the lowest MAC address. Once the route is chosen, it turns all of its ports facing the other switches in what's called a designated port. And this designated switch has to determine... A designated port always forwards frames. The switches that connect to the root switch then assigns a port to be the root port, and this root port has the best cost to reach the root. Now, the cost of a port is based upon its speed. So if you have a 10 meg link, it's going to be a higher cost, 100 meg, 1 gig. They start becoming lower and lower, so lower cost is better. And once a root is found, then the next port that is between the non-root switch has to determine if it will be a designated port or a blocked port. So this is also based on cost to the root of the port. If those are the same, it is then based on MAC address of the switch. The ports have to move into a forwarding state from a blocking state. It does this through a process of listening and learning. When a port is listening, it will look at all the MAC addresses, but it won't save any. It's still blocking at this time. And this listening state lasts for 15 seconds. After that 15 seconds, the port goes into a learning state. In this state, it starts adding MAC addresses to its CAM table, but it's still in a blocking state. The learning state also lasts 15 seconds. After this, all the ports can move into a forwarding state. So this can be a pretty time-consuming process, 30 seconds. So now this has been a lot of talk about how switch works, how spanning tree protocol works, but how do we configure anything? Well, on Cisco switches, per VLAN spanning tree is automatically configured. The switch automatically enables this feature and will run spanning tree. We can see this by using this command in exec mode, show spanning tree. So this command will state which switch is the root bridge as well. If you look, it says this bridge is the root. And if we do it on, say, another switch, it will show us what port has the root. So this isn't the root, but the one that connects off of this port is the root, which we know is this switch 1. So this shows spanning tree settings for all VLANs. So we can see what ports are forwarding, if it's going to be in a block state, if it's going to be in this forwarding state. But like I said, this is for every VLAN. So here's VLAN 20, VLAN 10. A command we can use to narrow things down if we only want to look at one VLAN is the command show spanning tree VLAN 10, or whatever VLAN. And this shows just VLAN 10. Another useful command is if we want to use the spanning tree, if we want to know the spanning tree status of an individual port. So that command is show spanning tree interface ET32. So it's a designated port, it's forwarding, and that's the cost of the port. So we can see how that port looks for the different VLANs shown, the 3 VLANs. Now, we can configure a few things, like we can adjust the hello interval, the listening and learning times, as well as the max age before it thinks the switch is gone. The default hello time is 2 seconds and can be changed to 1 second up to 10 seconds. And to make that change, we have to go in config mode, spanning tree VLAN 10. So this is, like I said, per VLAN, hello time 1. Or like I said, anything between 1 and 10 seconds. And like I said, also the default listening and learning time is 15 seconds. This can be lowered to as little as 4 seconds using the global command spanning tree VLAN 10 forward time 4. or any time between 4 and 30 seconds. So this will then lower the forward time. The catch with changing these timers is this must occur on the root bridge, and the other switches in the environment will then use that time. To adjust the max age time, the time it takes for a switch to consider the neighbor down after not receiving that BPDU, you have to use the command spanning tree VLAN 10 max age 6, or any time between 6 and 40. So a way we can verify this is to do the show spanning tree VLAN 10. And here we see the times have changed. A hello time of 1, a max age of 6, and the forward delay of 4 seconds, which is that listening and learning time. And just to show that it's transferring to our other switches, let's type, because right now we see it as 2, 20, and 15. Let's do show spanning tree VLAN 10. And here we're now set to 1, 6, and 4. Okay, so the next thing that can and should be altered is the placement of the root bridge. Now the root bridge is generally going to be, on a core distribution type switch that has more power than your standard access switches. Like I previously stated, the root is chosen either through a priority that can be configured or a MAC address of the bridge. Since the MAC address is fixed, the priority will have to be adjusted to select the root. So to adjust the priority, we'll make switch 2 the root. We can use under global config mode, spanning tree VLAN 10 priority 4096. So now if we do show spanning tree VLAN 10, this is now the root bridge. And if you see, now we reverted back to the original timers because we didn't change the timers on this switch, and this is now the root. Alright, so this number has to be in increments of 4096. So 0, 4096, 8192, 12288, etc. A nice feature on the iOS is if you type the command and choose a priority that is wrong, it will list all the priorities, and the lowest priority is the root. So let's just type a wrong one in. VLAN 10, we'll do 20. Priority, 2312. See, it's showing that it's incorrect, and here's some that you could use. There's also another command that is really nice. It works kind of like a macro. It will go out and see what the priority is currently set to and set itself as the root. So let's do that for that VLAN 20. Spanning tree VLAN 20 root primary. So, and in most networks, the distribution core areas of the network is redundant. So there are two switches. Once the primary is chosen, the other switch can be configured as the secondary root in case of a failure on that primary switch. And that way, it prevents a access switch from trying to become root if there was an issue. So let's set it on switch 3. Spanning tree VLAN 20 root secondary. Now, to verify the root command, we can use the show spanning tree root detail. Now it will say if the root is local, or give the root port and the MAC address of the root switch. Also using the standard show spanning tree commands above can also be used to find this, like the show spanning tree VLAN 10. Now the final thing to cover would be how to manipulate which ports we may want to use if we have multiple links between switches. So if there are, say, 2 links connecting a switch, one will go into a blocking state. Now by default, if one is a 1 gig port and the other is a 100 meg port, the 1 gig is going to be chosen as the root port, because the cost for that is better. There are documents online that will show the actual cost if you're interested, but the faster the port, the lower the cost. So the lower cost will win, but if we want to make the 100 meg the port to use, well, we can configure the port cost. So to do this, we'll go into the interface subconfig mode. So we'll go into interface T32, and the command is spanning tree VLAN 20 cost 5. And then to verify this cost change, what we'll do is we'll go and type the show spanning tree VLAN 20. And you can see here the cost is 5 now. So this has been a lot to cover. So in my next video, I'm going to go into more of the enhancements we can make to spanning tree to make it run even better. So thanks for sticking around, and I'll see you next time.